Suppose f is a function from a to b, and c is a subset of a. The set f intersects c times b, which is a relation from c to b, is called the restriction of f to c, and is sometimes denoted by f with this harpoon and then a c afterwards. So in other words, we're defining this new symbol in between an f and a c to mean take f intersect c times b. And all right, so let's try and draw a picture of this before we even read what the question is. We have a set A and a set B with a function f from a to b. Okay, and then we have a subset C inside of A. And so maybe my C will be this lower half of A here. And we're trying to restrict the function f to C. Okay, so we know that normally for every element in A, we have sort of exactly one arrow from A over to somewhere in the set B. And we're only going to keep the arrows for the elements in C here. Okay, so maybe there's just one element up here, and maybe there's a couple down here in C. And so these three arrows, or these three ordered pairs altogether, would make up F. And now we're trying to restrict that so that the domain becomes C. So we're just going to keep these two arrows for our new function. Okay, this new function we're calling f restricted to C, let's say. Another common notation for this, which you may have seen before, is sort of f with a vertical bar and then a little c subscript down here. Okay, that's another way to write f restricted to C. So basically it's the same function, but we're restricting the domain down to C. You've probably done something like this with trying to define inverse trig functions and so forth in the past. Alright, so what's the question? Prove that prove that this restriction is in fact a function from C to B, and moreover that for every C in this domain, capital C, the value of the original function is the same as the value of the new function. Alright, well that's kind of the point of the restriction, but let's check that it does follow from this definition we've made. Alright, so I have the proof over here on the right side already. You can sort of go back and forth if you like. In this video I'm only going to go through the sort of givens and goals here. So we start out with knowing that f is a function from a to b and that we have some subset C of A, and we're trying to prove that f restricted to C is a function from C to B. Okay. Now by definition up here we know what f restricted to C is. It's f intersected with C times B, and so that's what we want to show as a function. And to show something's a function, well, first of all, we have to show that it's a relation, right? So it's a subset of C times B, and then we have to show that for every C in the domain, there exists a unique B in the set B such that that ordered pair is in F, right? Or that arrow is in F. All right, and well, we have a function we're starting with too, and so we know that F it's a relation from A to B, so it's a subset of A times B. And we have this same definition, what it means for f to be a function. Okay. And I've used the same letter B here because that's the set B, but I've used a different letter A because that's in A. It might not necessarily be in C. Okay. So we know C is a subset of A, so we have the definition of that. And we already know that this is the case, right? I mean, f intersect C times B, that's definitely a subset of C times B. Okay, so that one, if you look over my proof, I just say we see immediately that this is a subset of C times B. Okay, so it's at least a relation from C to B. The harder work is showing that indeed it's a function. All right, so to prove this statement, we'll let C be an arbitrary element of capital C. Bring that over as a given. And we need to prove this. There exists a unique statement. Now that we have an element of C, we can use the fact that C is a subset of A, which has this definition, and to deduce that this is an element of the set A as well. Okay. So there's our universal instantiation, and then modus ponens gives us that this C is in the larger set A. Okay, and now we had this other universal statement up here from the fact that f was a function, and if we do universal instantiation there where we let little a be c, then we can keep this statement here with replacing the little a by little c, and we get exactly what we want, right? We've found well, yeah, that's exactly the statement that it gives us. I'll just leave it at that. So in my proof, I have written, well, because C is a subset of A, it follows that C is an A. And then because f is a function from A to B, right, which is where this statement came from, we know there does exist a unique B and B such that, well, that's a typo, isn't it? Such that CB, let me fix that, CB is in F, okay? Excellent. So there we go. Okay. All right. So that takes care of the first part, proving that it's a function. But now we want to actually show that it has the same values as the original function does. Okay. For you know, all little c in the set capital C. So here's our new goal. And to prove that universal, we'll let C be an arbitrary element of capital C. And we have to prove that these two numbers are equal. Okay, and the fancy way to do that is to say, well, let's just think of this as a number and this as a function. We've already proved it's a function. And this as an input, right? So when we apply this function to this input, getting that output, that means that this ordered pair is an element of that function. Okay. So that just comes from the definition of this, you know, function of input notation. Okay, so that we can let that be our goal, and that's nice. I mean, that's just saying this is an element of a set. So, so in order to prove that, well, what is this set? It's defined in our problem statement. We can replace it by f intersect c times b. And so we've got to show that this ordered pair is in F and it's in C times B. Neither of these are too hard. Let's just think them through. So as in the past, because C is in C and capital C is a subset of A, we could do, I guess, what was it? A universal instantiation of modus ponens got us to the fact that C is in capital A. So let's not repeat all that again. We'll just say that we know that. And why do I want to know that? Well, combine that with the fact that f is a function from A to B. I'm basically saying that C is an element of the domain of that function, and so if I have an input of C, then I have some output f of C from that function. And by definition of this f of C notation, that ordered pair is in the function f, right? So how did I say that over here? So C is in A, the domain of F, therefore this ordered pair is in F by definition of f of C. Okay, great. So, okay, and then we're still aiming for this last goal here. And for that I need to know that C is in C, which I already have. And I also need to know that f of C is in B. And so for that, well, if C is in A and this is a function from A to B, then the image of C under F has to be in the second set B, right? So, oh, okay, well, I already mentioned that one, that we have that goal. And for the second goal, this is all we need, that C is in C and f of C is in B. Okay, great. So that takes care of part A. So if you want to read through this proof, go ahead and pause the video. I will go on to work on part B next. So this problem has to do with trying to identify what f restricted to C is. Okay, maybe you have a function g from C to B which you think might be the restriction of f to C, and you want to actually prove that it is. You want to prove that it's equal to that restriction. Okay, and when this problem says, well, it's enough to just check that as long as you know g is a function from C to B, it's enough to just check that it's a subset of f, and then you know for sure that it's actually the restriction of f to C. Okay, so that's another pretty intuitively reasonable statement, but that's although maybe a little bit mysterious, right? Why just subset? So let's see how we can get it. Okay, we have the original given that f is a function from a to b, and I'm going to go ahead and, as stated in the problem, suppose g is a function from c to b, and c is a subset of a, and this is my goal. Right? It's a biconditional if and only if goal. And so we have a couple directions, and here I've already gone ahead and replaced this harpoon notation by f intersects c times b in both places. So we have the two directions, which I have indicated by my two arrows over here in the proof. Those are optional, of course, but sometimes it's nice to write them. All right, and for this direction, well, for that direction, it's clear, right? G is f intersects something, and therefore it's definitely a subset of f. So I said if G is equal to this, then we clearly have G as a subset of f. Okay. And for the second goal, we'll do direct proof. So suppose G is a subset of f, and let's prove that it is actually the restriction of f. And what does that mean? Right? This is saying that that these two functions are equal. Okay. And functions are the relations, right? They're sets of ordered pairs. So, oh, pardon me. How are we doing this? We're saying that, okay, we're using a theorem that we proved earlier, which says that two functions are equal if and only if, whenever you plug in any c from the domain into the two functions, you always get the same output. Okay. So G maps c to the same thing that this other function maps c to. So, okay, using that theorem, it suffices to prove this statement. Functions are the same if they always give the same output for when you feed in the same input. Okay, so let's let c be an arbitrary element of c, and then we're going to prove that these two outputs are equal, these two numbers are equal. And now we have to make a decision, right? Let's see, I know that G is a subset of f, and so I probably want to think of this as the function and this as the input, and then this whole side as the output, right? Because then what's that going to look like? And that's equivalent to saying that with this input and that output, that ordered pair is an element of this function, right? So that's probably something I can prove because I'm just looking at the order of things that I have over here. I mean, I could have thought of G as the function instead, and then tried to prove that, C f intersect C times B of C is an element of this function G, but I don't think that's what I'm going to be able to prove. Okay, so I've chosen this one. If you get the wrong one the first time, you just try again the other way. Okay, and so I got to show that it's in both of these sets. It's in F and it's in C times B. And, well, what can I deduce? Because G is a function from C to B, and I have an element little c in the domain, that means that I do have this ordered pair, C, G of C, in the function G. And then if I combine that with the fact that G is a subset of F, I get my first goal, that this ordered pair is in F. And using these two, I get that, well, C is in capital C, and G of C is in the second set here, capital B, and that gives me that the ordered pair is in C times B. Okay. All right, that brings us to part C, which is going to be basically an application of part B. We will let G and H be the two functions below. So G is a function from Z to R, which consists of ordered pairs in Z times R, satisfying this condition that Y has to equal 2x plus 3. And H is quite similar, but its domain is a set of all real numbers. Okay, so you see the ordered pairs are in a different Cartesian product as well. And it might be helpful to understand what the graphs of these functions would look like. Right? The function h, I mean, that's just what you've been drawing for years. So it's just the line y equals 2x plus 3. So there's a vertical intercept of 3 here and a slope of 2. So if I go over 1, I go up 2. So I don't know if I can draw a straight line on this thing. Let's see. Whoa. Okay, you can humor me and pretend that that line is straight. That was better. Okay, so that line would be the set of all, displays all the ordered pairs in the function h. Whereas the function g, the first coordinate is only allowed to be in z, so it would be not that line, but just the points with integral x coordinates, right? So it would be these 2 points that I already drew, and there would also be the point -1, and I guess that was supposed to go through 1. It's supposed to be -1, 1, okay? 0, 3, 1, 5, and so on. It would be just a bunch of points on this line, sort of spaced out. And so when we restrict the function h, okay, so we're supposed to show that if you restrict the function h to a new domain of z, then you get exactly g. Okay, I mean, it really looks like exactly what's happening here. So, all right, but how do you prove this? Well, if you look at part B, it was exactly the situation, right? We started out with a function, well, before it was called f, but now it's h. That's what we start with. And then we define a new function g from a subset z, c of a, right? So the a in this situation is r, and c, the subset, is z, and b is these r's over here. Okay, so it said that, we'll know that g is, in this case, h restricted to z if and only if g is a subset of h. Okay, so all we need to really prove is that g is a subset of h, and then our result that g equals h restricted to the integers will follow from part B. All right, so I just wrote out the proof here. By part B, it suffices to show, as I just explained, that g is a subset of h. So let's suppose we have an element of g, which would be an ordered pair x, y. We've got to show that it's in h. And so if we have an ordered pair in g, we know that, well, it's in z times r, so we know that x is in z, y is in r, and we know that this condition is true, y equals 2x plus 3. Okay. And because z is a subset of the real numbers, for sure, we know that this x is also a real number. But then x and y are both real numbers, so x and y are in r times r, and this equation still holds, y equals 2x plus 3. And that's exactly what we need to know that this ordered pair xy is in h. Okay, so that is how we show that g is in fact the restriction of h to the integers. All right.